Okay, we are starting recording now. Um, okay, guys, had you all got your quiz 2 back? I sent it to you a while ago. Anybody has any questions on quiz 2? I think most of you guys did well with quiz 2. So this is the solution to quiz 2. I already posted it. Let me show you. It's this one. This is the solution to quiz number 2. It's not really long, as you can see. Okay, I think most of you guys got it right. Okay. Right, this week is week 4. So we're gonna go through this stuff here, which is on portfolio theory. Portfolio theory is different from what we learned so far. Okay, guys. And as I will explain in a minute, there are six different cases that we will consider under portfolio theory. And we will consider 4 of them this week and 2 of them next week, right? And the tutorial sheet for this week is this one here. This is the tutorial sheet for the class on Thursday this week. Okay, guys, you have any questions? So, if you have questions, just feel free to. By the way, the quiz 3 for next week, I'm sure you guys know the quiz for next week is, trying to find what is this one. It's this one here. This is the quiz. My computer is slow. All right, this is quiz 3 for next, which is due next Tuesday, 24th of November. I did questions like this. If you look at the week 2 classes, you will see I did a couple of questions similar to this, right? So please try to follow the solutions for those. So if you go to week 2, let me show you. This is week 1. This is week 2. So if you go to week 2, there are questions I think in this week, that is week 2, that's similar to the quiz number 3, right? So for example, if you look at the sheet here, namely question 11 and question 12 are similar to quiz number 3, right? And there are 4 types of solutions, those 2 questions. The type solutions, handwritten solutions, and the video tutorial solutions, and the video solutions in full. Right, so there are 4 types of solutions that you can look at for the 2 questions, right? Okay, guys, any questions you guys have so far? No questions. Sorry, what am I doing? All right, now let me try to adjust the camera. The camera needs adjusting, guys. Okay, here we are. Now the first thing I want to talk about is feedback. Feedback on quiz 2. as I said, most of you done great with respect to quiz 2, but there are a couple of things I like to mention. You know, last week I talked about this. Let me know if you can't see my writing clearly. Is it focused okay, guys, or no? Right. This is known as the binomial series, and a lot of you guys used it, but I think the way you used it is not exactly correct, because remember, this series is true if a is a real number. But for example, if a is integer, if a is an integer, if a is an integer number, then this series will be 1 plus x power a equal to, the upper limit will be a, not infinity, right? And you should have known that from your calculus, or from your algebra you did in your past. And you should, this is the correct formula to use if a is an integer. In your case, a was an integer, guys. So you should have used, I didn't reduce any mark, but in the future, if you have a similar question and your a is an integer, then you should use this one, not this one, because this is true for a real number, okay? Like for example 1.5 or something, right? Okay. So like I think it was like in your case you had something like one, like this, right? This is what you had. So for this you should use this formula. So this will be the sum I from 0 to 2 of 2 choose I 1 over k to the power I, all right? And this would be, when I is 0, this would be 1. When I is 2, it will be this. And when I is 2, it will be, when I is 1 is this. When I is 2, it will be 1 over k squared. So there will only be 3 terms. So you will have only 3 terms in the series. Apart from that, all right, now let's move on to the next chapter, which is, as I said, is on possibility theory. Um, Portfolio theory is about, all right, this is basically the stuff I wrote earlier. A portfolio theory is when you have a portfolio, which is a collection of investments. By the way, can you read this? Okay, if it's not focused enough, let me know. So when I say portfolio, I mean, for example, like if you have portfolio of investments on gold, silver, copper, then that's one portfolio with three different investments. Or you could have investments on properties, like you could have investments on 1-bedroom apartments, or 2-bedroom apartments, or 3-bedroom apartments. So that's again a collection of investments, right? So these are 2 examples of a portfolio. All right. Now, in general, you can have any number of investments. So N could be, N in this case denotes the number of investments. And these are variables that denotes the loss. So X1 denotes the loss on the first investment, X2 denotes the loss on the second investment, X3 denotes the loss on the third investment, and so on until Xn denotes the loss on the nth investment, right? Now, what people are interested in obviously, you don't want to make a lot of loss. So the question is, how can you study the properties so that the amount of loss that you make as a portfolio is minimized. So that's what we're going to talk about in this chapter, right? Okay, so I'm going to consider 6 different cases. There are 6 possible cases that can occur in practice. The case 1 is the most simplistic, where the losses are IID. IID means independent and identically distributed, and the number of investments is a fixed number. The second case is where the losses are IID, but the number of investments is a random variable. And the third case is where the losses are INID. INID means independent but not identically distributed, and the number of investments is fixed. The fourth case is where the losses are INID and the number of investments is a random variable. And case 5 is where the losses are dependent, because in practice, the losses are not likely to be independent. So for example, if you're investing on say 1-bedroom or 2-bedroom and 3-bedroom apartments, the losses on 1-bedroom apartments are likely to affect the losses on the 2-bedroom apartments, and so on. Right? So these two, case 5 and case 6, are kind of more realistic. Okay, you should know what I'm saying. So case 5 is where the losses are dependent random variables and the number of investments is fixed. And case 6 is where the losses are dependent variables and the number of investments is a random variable. So what we're going to do in the next couple of weeks or so is to talk about each of these 6 cases and talk about the variables of interest, right? Okay. So I will talk about three. I mean, there are many variables of interest. I mean, we could have a whole course about. We can have a whole course about different variables, right? But here I will talk only about 3 different variables. The first one is the sum of the n losses. So it's obviously known as the total portfolio loss. So that's a really important quantity. So you like to model the portfolio so that the values of S are minimized, right? You don't want to have a total portfolio loss, something huge, right? Okay, and the second one is the minimum of the losses. So it's known as the minimum portfolio loss. So in this case, this gives you an idea about which of the n portfolios has the lowest risk. You should know what I'm saying. Because you have n different investments, and you want to know like which of the n investments has the smallest risk or smallest loss, so that you can be good with it, right? And the next one, this is the maximum or the maximum portfolio loss. So here you're asking the opposite question. If you have an investment, you want to know which of the investments has the largest risk or the largest loss. So next time you try to a different investment which is not so bad, right? So these are 3 of the variables I will talk about. Okay, so each of the 6 cases. So now I don't know whether you guys looked at whether you had time to look at the videos for week 4. I did like I think I did, including this video, I did 4 videos or 5 videos. All right, but I'm not going to go through them. So I'm just, what I would do, what I will do now is to do some examples. I think you can go through the videos in your own time. I think it would be a good way to learn about the videos is to do examples. So I will start with example 1. Okay, example 1. Suppose please let me know if you can't read my writing clear. Okay. Okay. So you have n x1 to xn are the losses. They are assumed to be IID with exponentially distributed with parameter a. We want to find the distributions of U. So remember, U is the minimum portfolio loss, V is the maximum portfolio loss. Okay. So let's do that first. So the okay, I'm gonna write this as the probability 1 minus the probability that capital U is greater than little u. All right, so this is gonna be 1 minus the probability that the minimum of x1 to xn is greater than u. Okay. Now, if the minimum is greater, then each of these guys has to be greater, right? So this is gonna be 1 minus okay. Now, because of independence, because we are assuming this IID, which means which includes independence, right? So this is gonna be 1 minus okay. Now, because each of these have the same distribution, we are assuming exponential with parameter a. So this is 1 minus the probability that to the power n, okay. Now this you can write as 1 minus the probability that x1 is less than or equal to u, okay, and this is 1 minus this for the exponential distribution. I'm sure you guys know this is the CDF of x at u, which for the exponential distribution is 1 minus okay. All right, so if you simplify the 1 and the 1 cancel out, so this will be a u n. All right, so this is the CDF of U. All right, so the PDF of U is just the derivative of this. So this is gonna be, if you differentiate this with respect to U, you get AN E minus A N U. All right, so this is the PDF of U, right? Okay, guys. Okay, so that completes finds the distribution of U. So the next thing I want to find is the distribution of V, which is the maximum portfolio loss, right? So let's start with that. So the CDF of V is the probability that capital V is less than or equal to little v, and this is the probability that the maximum right. Okay, guys. Now, if the maximum is less than or equal to this, then each of these guys has to be. All right, so that means x1 less than or equal to v up to xn less than or equal to v, right? Now, because of independence, you can say that this is the same as the probability that okay, guys. Now we know each of these guys is the same because they have IID, right? So this is the same as the probability that x1 is less than or equal to v. Everything raised to power n. Okay, guys. Sorry, excuse me. So this is the CDF of x1 at v, which we know is 1 minus, okay, this to the power n. All right, so this gives you the CDF of the maximum portfolio loss. Now the PDF of the maximum of the maximum portfolio loss is the derivative of this. All right, so you should differentiate this with respect to v. You get this is what you get. All right, so is it clear? Any questions so far, guys? All right, so in this example, we worked out the distributions of the minimum and the maximum portfolio losses, right, given, right? All right, now let's look at an example. So this is example 2. Example 2. Right, so in this case, you have losses the same as in example one, but the number of losses, which I denoted by capital N here, has a geometric distribution with parameter p, and we are assuming that the losses and the number of investments are independent random variable. Okay. Okay. So the question is to find the distributions of U and V. Okay. Right. Now to find let's start with the first one, the city, the U. Which is, I'm going to denote by this, which is the probability that capital U is less than equal to little u. Right? Now, I'm gonna write this as, well, there's no need to do that. All right, I'm gonna write this as follows. This is known as the total probability rule. I'm sure you learned this in your first year probability course a long time ago. You may this is known as the, if you don't remember what it is, I think I mentioned this in the videos too. This is the total probability rule. All right, that is because n is a random variable, right? You cannot continue unless you condition on capital N. So that's what I've done here. Now, if you look at this conditional probability, this conditional probability is exactly what we did in example one. So using the result of example one, this one we already know what it is, right? And if you look back, you should look back at what we did for the CDF of U in example one. You will see this. Right? This is what we got for the CDF of U under example one, times n. N is we are assuming is a geometric variable, right, with parameter p, and so this is going to be p times 1 minus p to the power n minus 1. All right, you follow me, guys? So this is the PMF of the geometric variable, you should recall. Okay, now this, you can write it as two different sums. Okay, and minus, right, and here you can take the p outside, and you can take e to the au outside. Then you have inside the sum from 1 to infinity, you have e to the minus au times 1 minus p to the power n minus 1. Okay. All right. So you have, correct me if I'm wrong, I think I did this right. Just a minute, let me check. Minus NAU plus AU. So it should be negative here. Okay. And all right, in the next step, the sum of all the PMFs must add up to 1. So this is 1 minus P E of minus AU. Now I'm gonna make a substitution. Let's say M equal to n minus 1. Okay, I'm just making a substitution. So under this substitution, this will become M from 0 to infinity of E of minus AU 1 minus P to the power n. Okay. All right, you guys following me so far? Any questions? Okay. Now what you have here is a geometric sum. What you have here is a geometric sum. So using the formula for the geometric sum, I think which I mentioned, I might have mentioned this before, but using the formula for the geometric sum, this you can write as 1 divided by 1 minus E of minus AU 1 minus P. So this is, now if you don't remember this, I will write it down using the fact that if you have something like M from 0 to infinity of x power m, then this is 1 divided by 1 minus x. So this is the, I'm sure you've seen this before, guys. This is the formula for the sum of a geometric series. All right, so we have shown guys that the CDF of U is equal to something like this, right? Okay, guys. Are you any questions so far, guys? All right. So that's U. Obviously, you can also find the PDF by differentiating this. I will leave that. I will leave that for you guys to do, right? Right. The next thing I want to find is the CDF of V. The CDF of V is this, and this is the probability that capital V is less than or equal to little v, right? And this, I'm going to use the total probability rule one more time. So I'm going to say this is equal to okay. All right, guys. So once again, I have used in this line here the total probability rule, right? Okay, in the next line, I'm going to use what we got in example 1. You may recall in the previous example, we found out that this guy here, this is the conditional probability of V, the maximum portfolio loss, given that the number of investments is fixed. And we got that. If you look at what we got, in example 1, this is what we got. okay, for this one, okay, and this multiplied by this probability, which is p times 1 minus p n minus 1. This is the PMF of the geometric variable, okay. Now I'm going to pull out certain factors outside. So I'm going to pull out the p factor. Then you have this sum, and all right. Okay. Now in the next line, I'm going to make the substitution that m equal to n minus 1. You will know why I'm doing this. So this will be so under this substitution, the sum will go from 0 to infinity, right, of okay, of this, right. All right, now again you have what you have here is a geometric series, so you can use the formula for the geometric series I gave you in the previous slide. So this will be excuse me, multiplied by okay. All right, so this finds this completes example 2. So here we have found the distribution of the minimum and the maximum portfolio losses when the number of investments is not fixed, it's a random variable. Okay. Any questions here so far, guys? Any questions on the two examples? All right, guys. So that's example. All right. Let's try. If I have time, let's try and do one more example. So this is the next example I'm going to consider is example 3. So suppose sorry, little m. This should say little m. Right. So here we have a case where the losses are no longer identically distributed. So the losses are the exponential distribution with parameter ai, I from 1 to n, right? So let's see. So this is case 3, basically the case 3 of the 6 cases I talked about earlier. So let's see how what we can do. So to find the CDF of U, which is the minimum portfolio loss, you can write it like this, less than equal to U, and this you can write as 1 minus the probability that capital U is greater than U, and this is 1 minus the probability that the minimum of x1, excuse me, x1 to xn is greater than U. Now, if each of these guys is greater than, then this is the same as saying that the probability that x1 is greater than U up to xn is greater than U. Now, we still have independence. I mean, we are still assuming that the losses are independent, only that they are not identical. So we can write this as the probability x1 greater than U up to the product of all the n probabilities, right? All right, now this you can write as 1 minus. This guy here you can write as 1 minus the probability that x1 is less than or equal to U, all right? And this one you can write as okay, right? Now we know that since x1 is an exponential random variable, this guy we know is 1 minus e minus a1 u, all right? And similarly, the last term yeah. So the 1 and the 1 cancel, and the same thing here, right? So what you get is 1 minus e of minus a1u up to e of minus a-nu, right? So it's basically you have 1 minus e a1, the sum of all the a's times u. So this is the this is the CDF of U, the minimum portfolio loss, when the losses are exponentially distributed, but not identically distributed, right? Okay. So this is the so the PDF. Any questions, let me know. Just feel free to use the chat box, guys, or talk to me using a microphone. So the PDF of U is just the derivative of this with respect to U. So that will be, if you differentiate this with respect to U, you will get all right. Okay, guys, I know some of the screen is not clear, but okay. So this is the density function of the minimum portfolio loss. Okay. All right. So that's U. Now the next thing The next thing I want to find out is the V. So the CDF of V. Remember, V is the maximum. Is okay. It's this one. This you can write as the probability that capital V is less than equal to V. Yeah. And this you can write as the probability that the maximum of x1 to xn is less than equal to V. Yeah. Now, if the maximum is less, then each of the variables has to be less than equal to. Yeah. Now, because of independence, because you're still assuming that the variables are independent, I mean, the losses are independent. So you can write this as okay. Now this guy is the CDF of x1 at V, which is, I'm sure you guys know, is E1 minus E minus A1 times V, right? And this guy is the CDF of xn at V, which is 1 minus E. Okay. All right, guys. So now this, if you like, you can write it as product I from 1 to n, I from 1 to n of all right. Okay, guys. And so this is the CDF. Now, if you want to find the PDF, if you want to find the PDF of V, you just need to differentiate. You need to differentiate this with respect to V. Now, this is where the product rule comes in. You may recall like when you have what you have here is a product of n functions, and you should one of this you should go to the YouTube channel or the course website. There is a formula I gave you for differentiating a product of n functions. I think it's under the section called preliminary section. You should go to the preliminary section. You will see a formula for that. And if you use that formula, this is what you will get. I hope you remember the formula that I gave you. Okay. All right. So this is the formula that I gave you for differentiating the product of n terms. So that's what I have used here to get it. Okay. So this completes example 3, right? So when you guys come on Thursday, unless you have questions now, you can also ask me right now. But on Thursday this week, I will go through the tutorial sheet. I think I mentioned that already. Let me mention that one more time. So you should go to the here we are. So if you go to week 4, which is this one, this is the tutorial sheet for day after tomorrow. And here we are. Okay, this is the one. All right. You won't be able to do 6 and 7, but you should be able to do the other parts. So when you have time, try and do the other 6 parts. You will not be able to do part 6 or part 7. Okay, guys. And any questions you'd like to ask me now? Maybe we still have about 10 minutes, but I mean, well, it's time up, but I still like to know if you have questions. Hello, guys. You have questions now? And anything about, I mean, about in general about the course or about the next? No? Is everything okay? I hope everything is okay with you guys too, wherever you are. I mean, I'm still in Manchester and I have, as you can see from my voice, I have the COVID, only mild one, but I don't think it will get serious, but yeah. Okay, so anyway, take care wherever you are, and I'll talk to you guys on Thursday. And if you want to contact me before that, you know how to do it. Okay. All right. Have a good evening or wherever you are.